Hi, my name is Yair Noam. This work is done together with Andrea Goldsmith. She's my advisor. I'm a postdoc at Stanford in her group. And the work is about blind null-space learning or interference mitigation in MIMO cognitive radio. And this is what I'm going to show. So cognitive radio, the idea in cognitive radio is to allow secondary unlicensed user to coexist simultaneously in the same band with primary user. So this is a cognitive radio scenario. Here we have a secondary transmitter, a secondary receiver, and this is a primary transmitter, a primary receiver. And the secondary transmitter is causing interference to the primary receiver, and this is the interference channel to the primary receiver. And the secondary transmitter is allowed to transmit as long as the interference inflicted to the primary user is below some threshold. So this is one of the cognitive radio paradigm. This paradigm is called the underlay paradigm, and this is the paradigm that we deal in this work. And we do it in the framework of MIMO. So what is good about MIMO? Why MIMO is so important for cognitive radio? Why it is so attractive? Well, in the case of MIMO, the secondary transmitter if he knows the channel to the primary receiver, and he has more antenna than the primary receiver has, he can transmit in the null space of the interference channel to the primary receiver, and he actually, in this case, he becomes invisible to the primary receiver, and the rest of the signal, and he can use all the rest of the degrees of freedom to his benefit, without interfering to the primary user. So that makes a MIMO cognitive radio very, very attractive because it gives a spatial coexistence possibility. However, in order to do that, the secondary user need to know the interference channel to the primary user. And the question is, how can you obtain this information without any collaboration by the side of the primary user? Of course, if the primary user is willing to assist him in this task and help him in the channel estimation task, help him with the secondary user will transmit a training sequence, and the primary user will estimate and feed it back, then it is not a problem. But we would like the secondary user to learn this null space without any collaboration by the side of the primary user. And in this work, we show that this is possible under some mild conditions which are satisfied in many practical systems. So this is the setup that we are considering. What we have here is, this is the secondary transmitter. He wishes to learn this channel, and he has no cooperation by the side of the primary user at all. But we are making one assumption, and the assumption is that the primary user is using some transmission scheme which responds to the interference inflicted by other users in the system, in this case, the secondary user. So we assume that the primary user is increasing its, for example, if the secondary user is increasing its interference, the primary user will respond by instructing its transmission to increase the power, for example. And the secondary user will be able to detect that by measuring the energy of the signal Y2. So this is how it works. This is not the only way to do it. The secondary user can extract this information by listening to the primary user control channel or whatever. But the assumption that we are making here is that the secondary user is able to know whether he increased or decreased the interference to the primary user. So this is the assumption that we are making. So from this, so how can we, in this case, how can we learn the interference channel to the primary user? We can do that if we knew the singular value decomposition of the matrix H12, and actually we are not really interested in the singular value decomposition of the matrix H12. We are only interested in the right term of the singular vector in this decomposition, and we are only interested in those vectors which correspond to the null space. Now, we do not necessarily even have to obtain the singular value decomposition. We can obtain the eigenvalue decomposition of the matrix G, which is the multiplication of H Hermite times H, because they have the same null space. So we are actually interested in diagonalizing this matrix G. Now, how can we do that? Well, if we knew this matrix, which we don't, we could have applied the Jacobi technique. What is the Jacobi technique? The Jacobi technique generates a series of two-dimensional rotations. Each rotation is determined by two angles. One is theta and one is phi. And these rotation angles are chosen to zero the off-diagonal entries. So at the first phase, you zero these two entries, and at the second, you zero these two entries, and at the third, you zero these two entries. And in each step, you choose the rotation angles according to this formula. The problem, of course, our problem is that we don't see this matrix. We can't see them, so we don't know how to choose these angles and how to realize the Jacobi method. The only thing we have access to is that we are transmitting a signal. This signal goes through the channel. It is being normed, and then it goes through some monotone function. And this is the only information that the secondary user has. So we would like to implement the Jacobi technique using only this information. So we have here two theorems that says that it is possible to do that. The first theorem that says that these angles can be obtained using a two-dimensional blind optimization. And every local minimum of this blind optimization is the absolute minimum, is the desired value. The second theorem says that the optimal values of the Jacobi technique can be obtained by two one-dimensional binary searches. So what it means that we can actually implement the Jacobi technique using binary searches, which is very, very simple and not complex, and that makes the entire thing practical. So what we have here is what we are doing is the secondary user is just, for each search in the binary search, it transmits signal, and then he measures the effect that this signal has on the primary transmitter, and then he's doing it again and again and again and again, and that's how he learns the null space. Here we have a theorem that says that the ultimate level of interference that the secondary user inflicts to the primary user is in the order of magnitude of the square of the accuracy of the line search. So what it means that we can determine what will be the level of interference to the primary user by the line search accuracy. And for example, if we are interested in reducing the interference by minus 15 dB, we just choose the accuracy of the line search to be minus 7 dB, which is very, very rough search. And here we have some simulation results. These simulation results show that in the case where the primary user has one antenna and the secondary user has two antennas, for example, the secondary user is able to reduce the interference to the primary user with 10 dB in only 8 transmission cycles. For example, in LTE, each transmission cycle may be just 1 millisecond, so he actually can mitigate the interference to the primary user within just 8 milliseconds. If the secondary user has 3 antennas, we see that in 25 transmission cycles, he can reduce the interference within minus 20 dB. And within 20 transmission cycles, he can reduce the interference within minus 15 dB. So in this case,
wrap it up. We got one thing.
Okay, so in this case, so this is actually very practical and can be accomplished in real scenario. The rest of the work is, I think that's it. I don't have enough time. Thank you very much.